Let's dig into the dot product. Let's dig into some honest to goodness, good vector calculus stuff. The dot product is something we will again use all year long. This will be unavoidable type stuff. We have to understand the dot product not just as a simple calculation, but as a greater concept and a greater relationship. So through these notes, I hope to share that with you. Not only how do I just calculate it, but what does it mean? How can I conceptualize what it does? Because it took a long time for me to really put these pieces together, so hopefully I can synthesize that for you folks. The idea here, or the question is it possible to multiply two vectors and get a meaningful result? And the answer is yes, in two ways. The first way is the dot product, and we'll focus on that today. The next lesson will be the cross product, and that's the other way. The biggest difference between these two is that the result of the dot product is a scalar. Please recognize that the result is scalar. That just means it's a coefficient, or you might think of it as a plain number, and not as a vector quantity, where the cross product results in a vector quantity. This results in just a plain number, and the calculations are about as straightforward or simple as you can imagine. I'm just multiplying I component by I component, j component by j component, k component by k component. We're just multiplying 2 times 6, or 2 times 3. 4 times negative 1. 6 minus 4 is 2. And you've just completed your first dot product. It's x component by x component. It's y component by y component. If I had it z component by z component and add up those resulting products. Same here. I don't need to be afraid of the fact that this is written not in my typical vector format, but rather in the component form. It's totally fine. 1i times no I is nothing. 2j times 2j is 4. Negative 3k times negative 1k is positive 3, and my result is 7. Just like that. Let's think about properties before we get into what this means, because it's not as straightforward as you might want it to be. What this means for us is, the properties, there's a bunch of them, and you'll kind of see them pop up. I'm not going to deal too in-depthly with them, but we will prove a little bit here. We will revisit them. So don't be surprised if I ask you to come and show me one of these things, that it actually works, and you would just do that by, like we did at the top, using generic terms, multiplying it out, and hopefully showing that they're the same thing. For instance, we're doing this a dot a is a squared. So if, let's just say that a has these components, a1, a2, a3, and if I'm doing a dot a, I would get a1, a2, a3 dot a1, a2, a3. When I'm multiplying those across, that gives me a1 squared plus a2 squared plus a3 squared. Because again, it's x component by x component, y component by y component, z component by z component. And those multiply to make these. Realizing it's a little zoomed out for me today. All right. Well, is that equal to the magnitude squared? Well, I know that the magnitude would be the square root of a1 squared plus a2 squared plus a3 squared. And so if I square both sides, I definitely end up with this. The magnitude of a squared is a1 squared plus a2 squared plus a3 squared. And we've now shown that these are the same things. Watch me run off the page like that. Not too crazy of a proof, just show that the left side reaches a point that the right side can also logically reach. This arrow should probably go across. But what is a dot product? But what is a dot product? The first thing is, the dot product is a way to multiply vectors into a meaningful quantity. right? We have these difficult data structures that are vectors that have multiple layers, one that is magnitude and one that is direction, and neither of which are absolutely obvious from the initial thing, right? Do I know the magnitude or direction of either of these? Just by staring at them, no way. I have to get involved and calculate them. So if I'm thinking, well, if I'm even struggling to conceptualize the layers of data that these hold, how am I going to combine them? Adding them makes sense because I'm just adding the directions. Subtracting them makes sense because I'm subtracting the directions or subtracting the magnitudes. But then when I get to these multiply, it's like I'm doing like a 2 by 2. I'm expanding dimension. You really have to stretch your mind to figure this out. But the better or more important definition I could give is that a dot product measures the extent that two vectors point in the same direction. And that's this best seen in this next box at the bottom. But let's just write it this way. The extent, we're going to find the angle between. So if a dot product helps me find an angle between, it helps me quantify how much two vectors point in the same direction. We'll kind of dance around this for a while and help us understand it. There is a bit of a proof for this thing that comes out. I'll make sure I link it in the modules. But there is a direct relationship between this and the law of cosines. But let's just memorize it. Let's just know that if I'm multiplying these two vectors, it's the same as the magnitudes multiplied by the cosine of the angle between. Right? In this case, no picture given, but if this was vector A and this was vector B, this is the angle we're discussing. The angle between these two vectors, how closely related are they? That is a cosine relationship. I cannot write this in big enough, bold enough letters. I cannot circle it or put enough stars next to it that the dot product is a cosine relationship. The dot product is a cosine relationship. Cosine is our x value. I'll keep that in mind as we keep working through. We have a nice recap at the bottom. We'll see some pictures here that help us describe that cosine relationship. But here we are. Find the angle between. Well, I'm just going to use that formula, which I'll write on the side again. A dot B over A magnitude times B magnitude is the same as cosine of my angle. A dot B is the same as the magnitudes multiplied makes our cosine. Dang, I should have said divided. How shameful. Here we are. Let's find our magnitudes real quick. I'm doing 2 squared plus 2 squared plus 1 squared. 4, 4, and 1 is 9. I square root that to get 3. I believe in you to take these magnitudes without me. That's 25, 9, and 4. That's the square root of 38. That doesn't get very nice, but it'll be all right. I don't really care. This is another situation where I can't always give you the nicest angles. It's not always going to work out so well. So don't be surprised when you get some ugly things. But the trig will take care of it. The trig will clean it up. So again, I'm setting this all up. A dot B. Let's do this A dot B calculation. A dot B. A dot B is going to give me 10 minus 6 minus 2. That gives me 2. So now I set the whole thing up in that calculation. We're looking at A dot B over magnitude A, magnitude B is going to make cosine theta. Is going to be 2 over 3 rad 38. Definitely not in the unit circle. Definitely not a value that I'd expect you to know. So you use that inverse trig function there and you get your nice angle somewhere around 88 degrees. All right. How about this? Prove that this vector is perpendicular, that's what that symbol means, this is perp, to that vector. Well, perpendicular means they make this shape. Perpendicular means they make a 90-degree angle. And what is the cosine of 90? Makes 0. Well, if I'm thinking about this fraction, is my denominator going to be 0? No. My numerator is going to be 0. So in this example, not only are we going to prove these two things are perpendicular, we're going to find a more general case where we can identify things are perpendicular all the time, and we will leverage this for equations of planes and lines and surfaces and tangents and things like that in the future. Let's do it. A dot B. A dot B is going to give me 2 times 5 is 10. 2 times negative 4 is minus 8. Negative 1 times 2 is minus 2. I got 0. That means A dot B over this quantity makes 0, which is equal to cosine theta, and that tells me that theta is 90 degrees. Just like that. And so I'll write this on the side in some nice text for us. If A dot B is 0, then A is perpendicular to B. Gotta have it. And we can use this inversely where it says, if I know this is equal to 0, then it's perpendicular. I could also say, hey, if I know A and B are going to be perpendicular, or if I'm forcing them to be perpendicular, I can force their dot product to be equal to 0. And we will heavily use that fact throughout this course. So let's work on that understanding of what a dot product is, because there's not really many more examples I can take beyond this. So let's work on understanding what a dot product shows us. Where does the dot product show up in a picture? Right? If I drew a picture of A and B, where does my dot product appear on this image? Well, let's see. I know that the dot product is involved with cosine. So if I'm thinking of this as some kind of right triangle, I know that if I label this A and H, cosine equals A over H. Well, in this case, A is how much of A goes, or how much of B goes in the direction of A. How much of B goes in the direction of A? If you Google what is a dot product, it tells you how much of B goes in the direction of A, or how much of A goes in the direction of B. And I find that so hard to conceptualize, but throughout this page we'll build that further. In this case, if I wanted to find this length A, I'm going to call it PS. So the magnitude or length of that vector from P to S is the base of this triangle. And now it runs along A. It's parallel to A, but it's definitely not equal to big A vector. My hypotenuse is B. This is PS. And so, if I want to know how much of B goes in the A direction, it turns into this, where I multiply both sides of this equation by that magnitude of B. And now I have that PS, or this distance at the bottom, the amount of component B that goes along A, the amount of B that goes in the A direction is this. The magnitude of B times the cosine of theta. And hopefully that makes sense for you, because the cosine is my horizontal component. In this case, I'm setting my horizon to be one of the vectors. So it's the amount that's headed in the direction of A, because I set A as my x-axis. I set A as my x direction. I call it D as a distance here, just to show this is a scalar quantity. what comes out is a number. It tells you just a number, just as a dot product gives you a number. And you can even see how closely this is related to your dot product. Very similar. It would just be multiplied a little bit. How about if I wanted to know in terms of a vector projection? If I wanted to turn this projection into a vector to figure out, hey, what direction is happening, I'm going to take this amount, this magnitude that I found up here, and I'm going to apply it in the A direction by making a unit vector. I'm going to make the unit vector A by taking A and dividing it by its magnitude. And then I'm going to multiply it by that length. So I'm going to take this A, I'm going to shrink it down to be A hat. And I know that A hat has a length of 1. Then I'm going to multiply that by the distance d to stretch it out to be this full length. And so my vector projection becomes d times A hat. That's what this is. D times A hat. I keep using D and PS interchangeably. Yeah, magnitude PS times A hat. So this would be a vector quantity. I'm applying it in the direction of A. The parent function, base unit, direction of A is A hat, which I get from that unit vector calculation here. How did I find how much of B, what portion of B goes in the direction of A? Well, I made it so that my cosine correlated with the base, and the cosine AH relationship took out the part of B that goes in the other direction and just left me with the part of B that heads in the same direction as A. Before I do this work example, let's hop down here and let's think a little bit more about that same direction, different direction. Because if I have two vectors that are basically headed in the same direction, the angle between them is approaching 0. Well, if my angle is approaching 0, then the cosine of that angle approaches 1. And that means this relationship approaches 1. We saw this on the other side. If these vectors are the same, these would be equal. We did this proof on the back side. A dot A is equal to the magnitude of A squared. The more similar these things are, the closer they get to 1. So even if I change this out for B, the closer these things are to being 1, the closer they are to heading in the same direction. So when you get to a dot product that's very similar to the magnitude, that's very similar to the size, they're basically headed in the same direction. If they're exactly equal, we know they're collinear, we know that they're parallel if there's no angle between them. If things are perpendicular, my angle approaches 90, then cosine approaches 0, and the dot product approaches 0. If things head in opposite directions, they're still parallel. However, they head in opposite directions. That flat angle approaches 180, therefore cosine approaches -1. And so that means that, again, my numerator and denominator are essentially equal, except one of these is very likely the opposite of the other. A is opposite likely -b, or -b is equal to A, -a is equal to B. These vectors are exactly the same, headed in opposite directions. So this approaches, -1. You can see how the cosine is equal to this, and the cosine is related to the angle and the juxtaposition of the two vectors and how they relate. Again, to recap one final time, the dot product is a scalar. It is a number. That number tells me the angle relationship between vectors. And in somewhere, in big, grand, bold letters, you should write that this is a cosine angle relationship. Not a sine angle relationship. We'll save that for cross product. It is a cosine angle relationship when it's a good thing that they head in the same direction because it maximizes the value. Whereas if they head in opposite directions, a dot product is minimized. It is giving zero value back. Just quickly to wrap this up, force, work. Work is force times distance. What if these are vector quantities? Freaking dot product them because work is a scalar value. Well, so I have some P to Q that I'm dragging this thing along. I have some force that I'm using to drag this box. I don't know if you want to say that it's a box tied to a string, a particle being pulled by gravity, all sorts of the same things. So I'm just going to dot them. But notice, dot product happens between two vector quantities. So that means I need to turn D into a vector. The displacement, or distance, has to turn into a vector. So I turn it into a vector. P to Q. I just count the change. I'm going +2. I'm going +5. I'm going +2. And this becomes my displacement. When I pull this particle, like inch by inch by inch along this thing, this is how much it changes. So when I'm doing this F dot D, I have my force, 3, 4, 5, from here. I'm going to dot it with that displacement vector, 2, 5, 2. And from there, it's just a simple calculation. 3 times 2 is 6. 4 times 5 is 20. 5 times 2 is 10. I've got 36. The amount of work done is 36. Whew. Dot product will be with you all year. It is a cosine relationship. A dot product results in a scalar, and it describes an angle relationship between the two vectors, where it is really happy and maximized when those two are headed in the same direction.